Alrighty. So, we kind of went over this briefly. We didn't look at examples last time, but we did talk about, how you can use your arc length formula and kind of build up on that to come up with your linear speed and angular speed formulas. And we had kind of briefly, gone over these examples from your handout. So let's take a look at an example from our textbook here. So I'll leave these formulas open, and then these, this is, problem number 65 from your textbook, as you can see. Okay, so this one, as you can see, we're talking about a carousel with a 50-foot diameter, makes 4 revolutions per minute. And of course, they're asking us to find in part A, the angular speed. And then of course, part B, they're asking us to find the linear speed. So let's take a look at, how we can go about doing this. So as you can see, they're definitely telling us, we are talking about a 50-foot diameter, and then we are talking about 4 revolutions per minute, which of course that is 4 RPMs. So that's something that we're going to have to use to basically help us come up with our, angular speed. So let's go ahead and very quickly take a look at that formula for angular speed. Sorry, not that. So, of course, you can see we need the central angle theta, and then we need the time t if you're going to come up with your angular speed. And so, of course, the idea is, okay, how do we find that theta and how do we find the t? So that's kind of what we need to be working on. So we'll go back over here. So I know some of you have already worked through this part of section 1.1. So anybody want to help me out here? Do you know what you would do in this case? Which, of course, your diameter is 50 foot. So that would make our radius half of that, right? Because the diameter is 2 times the radius. So if you take half of that, your radius is going to be 25 foot. So that may be a good starting point to think about. But anybody want to help me out here?
Would the, oh,
Go ahead.
well, Andrew just said it in the chat.
Yeah.
Yeah.
Yeah, so you have your RPMs because that's telling you how many circles you're making, right? So how many times around the, I guess, the carousel you are going, because they're asking you to find the angular speed, of course, of the carousel, and they're specifically telling you it's got to be in radians per minute. So keep that in mind as you're working through these calculations. Our angle measurement has to stay in radians and not in degrees. And, we kind of talked about this last time that usually by default, we want to keep those angles in radians measurement. So yeah, very good. So we basically have, as Andrew said, you take your radius and you multiply it into those 4 RPM. So that's of course going to come out to be 25 for the radius with times 4. And what will that end up giving us? Sorry. No, I skipped a step here, didn't I? Because I didn't do the 2 pi measurement here. Sorry, I apologize, guys. So not the radius, not yet. 4 RPMs multiplied by 2 pi. And can you tell me why we're using 2 pi over here?
2 pi is a full circle.
Yeah, very nice, because the full circle is 360 degrees, or in radians, it's 2 pi. So that will give you 8 pi. And then what do we do next?
Divide that by 1 minute. Right.
Okay, so that will give you the feet per minute, but what else do we need to do here?
Convert minutes to seconds.
Yeah, we will need to, no, actually you will leave that in minutes because that's what they want our measurement to be. So yeah, we can leave that, but this is actually where we multiply it with our radius, right? Because this is actually right now the 8 pi that you came up with is actually going to be your central angle, because that's your 4 RPMs, which means you're going around the circle 4 times. We know each circle is going to have a measurement of 2 pi. So that's your degree, right? Your angle in the center. So when you do 4 circles around times 2 pi, that's where you get the 8 pi. So remember, guys, this is actually your theta. And then you multiply that theta with your radius. And then, you know, of course, we're converting that into time. So that's going to be where you divide it by t. And this is where you're going to end up with 25 times 8 pi over 1 minute. And of course, this is going to be in feet. So 25 times 8 will end up giving us what? Go ahead, Lucy.
Isn't that linear speed? I thought that was the formula for linear speed.
You know,
I
I
thought
might,
for angular is just theta over time.
yeah, because I did the arc length, didn't I? Yeah, I'm doing the linear speed first. Sorry, I apologize. And it's funny, I do this every year because in the textbook, your formula for linear speed is given first. So that's how I've always done it. So thank you, Lucy. I appreciate that. So we're actually working on part B right now, guys. So 25 times 8 pi will end up giving us, you know, 25 times 8, of course, is going to be 200. So that's 200 pi. And then, of course, this is in feet per minute. So this is actually giving you the r times theta equals t. And as Lucy mentioned, you're actually looking at this. I'm going to change my color so you know I'm kind of looking at the handout in the textbook like now. Remember, your arc length is S equals R times theta. So that's kind of where this formula came from. So that's what we are calculating over here is your linear speed. So you can say this is R times theta over T, or you can say that's basically S over T, which of course comes out to be V for your linear speed. So that's kind of what we are looking at here. And you know, since this is an odd numbered problem, you can go ahead and verify that answer. So if you just take the 200 and multiply it with the pi key on your calculator, or you can use pi as 3.14 if you want an approximate answer, that's where you'll get that 628.3 feet from. So that's where that answer is coming up. So yeah, this is your linear speed. So literally just take the RPMs, multiply by 2 pi because you're going in a full circle. So that's why you keep that central angle at 2 pi. The RPMs tell you how many times around the circle you are going, and then multiply with that theta value with the radius, and you have your arc length basically, and arc length divided by time gives you your linear speed. So I'm going to save this and then clear my screen since we'll need to look at the angular speed over here. So now for the angular speed, and you can kind of see, you know, again, over here at the bottom, you have this little conversion going from linear speed to angular speed. So you can definitely use this formula over here, or of course you can see you have the central angle divided by time over here. So based on that, now that you have calculated that linear speed, can you tell me what the angular speed for this carousel will come out to be?
Eight pi.
8
per
pi?
minute?
Okay. Anybody else have that same answer or a different answer for part A? So here you're calculating the theta over time, right? So that's going to be omega, which is theta over time. So if you calculated theta like you did before, which would be your 4 RPMs times 2 pi over 1 minute, that would end up giving you 8 RPMs per minute. Or actually, since you multiplied it by 2 pi, it's actually just in radians. That's your central angle. So 8 radians per minute. So, and then this guy, of course, came out to be 200 pi, and that's feet per minute. And again, like I said, since this is an odd numbered problem, you are able to verify your answer for this. So honestly, you can find the angular speed first, you can find the linear speed first. It really doesn't matter in what order you do that. As you can see, it works out in either case. So this one was V equals S over T or R theta over T. So this was the only additional step here, was taking that radius of 25 and multiplying it by 8 pi, which gave you that 200 pi feet per minute. And you can see there are multiple different examples in your textbook. Of course, you'll see a couple different examples in your handout and then in your homework. So hopefully you should still be able to get good practice from out of this. But before we move on to the area of a sector, did you guys have any questions for me? All righty. So let's pick an example for area of a sector. And for that one, I actually picked this one here, number 67. So this one says a sprinkler on a golf green is set to spray water over a distance of 15 meters and to rotate through an angle of 150 degrees. There's a diagram that shows the region that can be irrigated with the sprinkler, and then of course find the area of the region, you know, where that irrigation from the sprinkler is happening. So again, if you look at your textbook, your handout, that's kind of what the sector will end up looking like, because, you know, just imagine if your sprinkler is placed right here, and, you know, whatever that distance that the water will cover, you know, from the sprinkler, that's going to give you your radius. Well, you know, if the sprinkler head is here, but this is how far that water is going. And then we know how that sprinkler makes that angular motion. So, you know, it's going to have that range of, okay, it's going to go from here to here. So basically the idea is, what is this central angle going to be? And they've given that to us over here, because they told us it is 150 degrees, and they're saying that the water is being sprayed over a distance of 15 meters, right? So that's going to give you your radius. So basically they're asking us to find this area where the sprinkler is going to irrigate, you know, the water. So if you look at your formula here, you know, this is basically derived from the area of a circle, but, you know, of course, we're not doing the entire circle here. So you've got your radius, you've got your central angle, and then the fraction of that 1/2, and that gives you your area of a sector. So very straightforward. A equals 1/2 r squared theta. So let's use that over here. So 1/2, you have a distance of 15 meters. So that's our radius. And then we have an angle of 150 degrees. So that's going to be our theta. So can you tell me what this area will come out to be? And for this one, what I would like you guys to do is, you know, kind of like we did last time, have your answers ready, put them in chat. And when I ask you to, you can send it. So just don't send your answer, just have it ready, you know, go ahead and calculate your number. And then I'd like to see what everybody came up with as their answer. So don't send it just yet. And they didn't really give us rounding instructions. So for now, let's do 2 decimal places. And then based on your homework, you know, if they need more or less, you can change it in your homework. And, you know, if you just need some extra guidance, you can obviously look through the example in your handout to kind of see how they did the example that you have there, and then, try to use that in your own problem. So you can see here, it's kind of the same type of example: sprinkler on a golf course, sprays over a distance of 70 feet, rotates to an angle of 120. And then you can see how they perform that calculation over here. So that's basically the same thing you're doing for your problem here. Okay, so just have your answer ready in the chat, and I'll just give you guys another couple seconds to wrap up your answers. All right, guys, go ahead and send me your answers. Okay, Lucy, Darren. Okay, Andrew, Savannah, okay. Alicia. All righty, perfect. Very nice, guys. Savannah, you were just off by a little bit, and I'm not sure if that was just a rounding thing or one of your numbers was incorrect, but close to what it is. But yeah, as you can see from the rest of the answers, you're just a little off. So you've got the 1/2, of course, from the formula. Our radius is 15, and of course, it's supposed to be radius squared. So that would be, 15 times 15, so 15 squared. And then what happens with the angle over here, guys? Did you leave it as 150?
You convert it to radians, right?
Yeah, exactly. You have to convert it to radian. So you will see nowhere in the instructions they said that, your angle has to be in radians. But again, if you look at that formula from your textbook, you will see that they tell us that your angle is measured in radians. So it's given to you over here in the formula, but they may not always say that in the problem itself. So that's one thing you really just have to keep in mind. So you do have the 150 degree, but then remember to convert it from degree to radians. We multiply the fraction of pi divided by 180 degrees. So since you're getting rid of degrees, the 180 goes on the bottom. If you were getting rid of radians, then the pi would go on the bottom. So that's the extra, factor you have to multiply when you put it into this formula. And, throw that into your calculator. So 1/2 times 15 squared times 150 times pi divided by 180. So, let the calculator do the hard work for you. And you will see approximately this comes out to be 294 point, and then, got a bunch of decimals after that, 5243113. And then, like I said, since we're rounding it to 2 decimal places, you have 0.524. So the 4 doesn't have any effect on the 2. So it will stay at 0.52. And then you guys did great, because this is an area, and area is always measured in square units. So it does come out to be meters square, or, m square, like some of you had in your answer. So yeah, perfect, guys. Good job. That's exactly what this answer will come out to be. Anybody have questions on this example over here? And from your answers, of course, it looked like that you guys were right on track, but just in case anybody had any questions. All righty. So make sure I save this, and I'll go ahead and clear this out. And like I said, you do have a couple examples, some problems that if you needed to do for practice, you can work this out. These grading quizzes problems that I have in the bottom, this was actually before we started using WebAssign, and this is when you guys were turning in your problems by hand. But those are still good problems to look at, because even the problems that I have picked in your homework assignments were kind of influenced by these homework problems from your textbook. So if you needed, just like I said, extra practice without having to mess up your grade, you can definitely look at these numbers in your handout and use those to find the problems in your textbook for extra practice. All right, guys, so this is the end of section 1.1. Now we'll get into section 1.2, and this is actually where we formally introduce unit circle to you guys, though, we've kind of talked about it a little bit as we started this chapter. So we're talking about, basically your unit circle means that the circle has a radius of 1. And you can see that right over here in this equation. So this is the equation of a circle. You have your x squared plus y squared, which tells you where your center is going to be. And in this case, your center is at 0, 0. And then on the other side, you have r squared, which is the square of your radius. So that actually tells us if r squared is equal to 1, that means the radius is also equal to 1. Because, if r squared is 1 and you take a square root on both sides, well, your radius will come out to be 1 as well. And in this case, we're only considering the positive root, because if you remember from college algebra, anytime you take a square root, you can actually get one positive and one negative root. But in this case, of course, since radius is a distance, we're only considering the positive root. So that tells us our radius is 1, and that's why you call it a unit circle. So that's kind of where, this equation is coming from. So obviously you can see when you look at the ordered pairs, if you are going from the center to this point, well, that's a distance of 1 on the x value. If you're going from the center to this point on the left, well, that's a distance of 1. But since you're going in the negative direction, of course, that becomes -1. So that's more of a direction thing. Same thing, go up or go down, you will see it is still a distance of +1 or -1, depending on your direction. So that's how you know it's a unit circle, you have a radius of 1. Now they are saying, and this is kind of neat, they're talking about, now imagine that you are wrapping a real number line around the circle. So, you can start at the line, and, depending on if you're going in the clockwise or counterclockwise direction, you're going to have your positive or negative number. So we know your positive numbers are going to be in the counterclockwise direction. And of course, negative numbers are going to be in the clockwise direction. So that's kind of how, you're thinking about how you're wrapping that number line. And you can kind of read more of the details. I don't want to spend too much time on that. You can read the textbook or you can read your handout to kind of see how that superimposition happens. But basically, that's kind of how we design those unit circles. And then as you saw in that image from your D2L, what that unit circle ends up looking like. But basically they're saying, each real number t that's wrapped around that circle, once you take that number line and wrap it around, they're saying each real number t also corresponds to a central angle, theta, in the standard position. So remember, standard position means the initial side of your angle is going to be on that positive x-axis, and then you go in the counterclockwise direction to come up with your terminal side. So that's your standard position, whose radian measure is t. With this interpretation of t, they're saying the arc length formula, where you have s equals r times theta, we know the radius is equal to 1, which in this case, of course, we're then saying s equals r, so that arc length is going to be the same as your radius. We are saying that's the real number t is the directional length of the arc, which will be intercepted by the angle. So this is all going to be in radians. And this actually gives rise to where we get into our trigonometric functions, but this is actually associated with our ordered pairs, our x and y coordinates, because if you are taking that circle and, you're finding a point on the circle and, imagine, of course, that you're putting that on top of a rectangular coordinate space, Well, then obviously we can have X and Y ordered pairs, right? So any point on the circle can correspond to X and Y on our rectangular coordinate system. So they're saying the coordinates X and Y are two functions of the real variable t. These coordinates are used to define the 6 trigonometric functions. So you actually have 3 main functions, which is the sine, cosine, and tangent. Cosecant, secant, and cotangent are actually reciprocal functions for these 3 main functions. So if you look at the definition over here, we are defining sine of that real number t as y. Since cosecant is its reciprocal, you will see the cosecant becomes 1 over y, because think about this. If we're saying sine t equals y, well, I can write that as y over 1. So when I take its reciprocal, well, that becomes 1 over y. Same thing with cosine of t. If cosine of t is x, think of that as a fraction as x over 1. So again, when I take its reciprocal, it becomes 1 over x. And then tangent, we actually define it as y over x. So when you take its reciprocal and you get the cotangent function, you end up with x over y. So literally, you're just flipping that fraction to get the reciprocal function. And then anything that's going to be in the denominator, we don't want those numbers to equal 0. So that's why you will say here, x is on the bottom. So we say x cannot be 0, y is on the bottom, y cannot be 0. So just be careful about that, as you're working through these functions. And so this is kind of where, we first introduced this idea of these 6 trigonometric functions. And as you can see, these are the abbreviations. So sine, cosine, tangent are those main 3 functions. And then the reciprocal of sine is cosecant. So S actually goes with C. So since sine begins with an S, its reciprocal begins with a C. Cosine is the main function. Its reciprocal is secant. So C goes with an S. And the easiest one, I think, is to remember that tangent and cotangent are reciprocal functions of each other because, of course, they both have the name tangent in them. But with the sine and cosine, it's really easy to remember since sine begins with an S, its reciprocal begins with a C, and that's actually cosecant, not cosine, because cosine is the main function. And then in that same way, cosine has a reciprocal which begins with an S, and that's the secant function. And I have actually included another handout. I don't think I actually opened it. Is it this one? Okay, this one here. Let me clear this out. So this one actually kind of helps you out a little bit also. And this is more in terms of a right triangle, and we'll be doing this later on, but this can actually also help you remember your 6 functions, the sine, cosine, tangent, cosecant, secant, and cotangent. And we'll get a little bit into this, but one thing I wanted to point out, and we'll again kind of get a little bit when we get into that right triangle trigonometry, just to remember the order of, how these functions, you can remember, what value it's going to be. Is that SOHCAHTOA? And I know one of you had mentioned that on the first day of class, that you had taken trig before, and that was something you were familiar with. So that should definitely work out for you. But the one thing I wanted to point out, since we're not quite ready to talk about the right triangle trigonometry here, is just to remember that order of the reciprocal or the inverse functions with the original functions. So sine goes with cosecant, cosine goes with secant, and of course tangent goes with cotangent. So just something to help you remember those reciprocal functions. So this is a supplemental handout that I had. I think I have included in D2L that you can look at. But let's come back to our textbook over here. So one thing that we need to keep in mind is, anywhere on those fractions, especially for tangent, cosecant, secant, and cotangent, where your denominators can potentially have zeros, that's where your functions will actually be undefined. Because remember, guys, division by 0 gives you undefined, and that's the same thing you're going to run into with these fractions over here. So anytime that x or y value becomes a 0 on the denominator, your function is going to be undefined. And it actually shows you right over here where that can happen. So if you look at this little paragraph here, they are saying that the tangent and the secant function are not defined at x equals 0. So this is, where your x is equal to 0. Let's move this guy up a little. So you can see x is going to be 0 over here and x is going to be 0. So this is the point where x is going to be 0. So that means your tangent and secant functions are not going to be defined over here. As an angle, this is actually pi over 2 over here. And then, of course, on the bottom, it's 3 pi over 2. So they're saying when your angle is going to be pi over 2, your tangent and secant functions are going to be undefined because that's where your x is in the denominator. When y is equal to 0, which of course would be these points over here, where your y value is equal to 0, that's when your cotangent and cosecant functions are going to be undefined. So that's actually going to be at the angle measurement of 0 and pi. So this angle over here is pi, this angle is 0. So that's where your cotangent and cosecant functions are going to be undefined. So just anywhere that you would see that, when x is going to be 0, that's why the tangent and the secant functions are undefined. When y is going to be 0, that's where your cotangent and cosecant functions are going to be undefined. And, again, like I said, the more you practice with this and the more problems you do, you will start remembering this. So don't be too scared that, oh my God, how am I going to remember this? It's kind of one of those things, practice makes you perfect. So you will actually get more comfortable at remembering these things. But for now, use your notes, use your handout, your textbook to help you out as you're working through these examples over here. And this one here is just kind of showing you, if you had to divide your unit circle into 8 equal parts, well, what each of those angles would end up looking like. So you can see, we're starting out with angle 0 here. This one over here would be the angle of pi over 4. This is angle pi over 2. This guy here is 3 pi over 4. This one, of course, is pi at 180 degrees. This angle would be 5 pi over 4. This one I told you would be 3 pi over 2, 7 pi over 4. And then, of course, when you come back to a full circle, you're at 2 pi. So that's kind of what they're talking about, is what those corresponding t values would be, which would, remember, they correspond to your angle measurement at that point with a unit circle. If you're breaking them up into 12 equal parts instead of 8, then of course your angles will become even smaller, and you can see what those angle measurements will look like when you change your circle into 12 equal parts, or break up your circle into 12 equal parts. So that's kind of what they're talking about here. And then they kind of get into calculation of showing you how they're coming up with these ordered pairs, on your circle. So how they came up with this square root of 2 over 2, positive or negative. Here with the 12 equal parts, they're kind of showing you, you have square root of 3 over 2, 1/2, positive or negative, how you're coming up with that. So that's kind of what they're showing you over here by using that equation of a circle with the radius of 1, and then how, if you are using the line y equals x, how that can translate into replacing the x with the y, and kind of using some algebra to solve basic equations and then come up with your values for x and y. So you do have this sort of an algebraic way of coming up with this, but we're actually going to deal with this in a more trigonometric way, and that's where we'll introduce the right angle triangle and talk about the SOHCAHTOA that I was showing you in that other handout. So just some examples to kind of walk you through in terms of how they're coming up with those values. And Savannah, this was the question that I believe you had asked me in your homework problem. So they're saying evaluate the 6 trigonometric functions at each real number. So they're saying, okay, if your angle measurement is pi over 6, what will those 6 trigonometric functions end up looking like? So let's take a look at this example here. So they're telling us your angle of pi over 6 corresponds to this point of x comma y, which is square root of 3 divided by 2 comma 1/2. And then another thing you should keep in mind is the order in which your ordered pairs are written in terms of your cosine and sine functions. So in traditional rectangular format, we know the first ordered pair, the first value is going to be x and the second one is going to be y. When you translate that to a unit circle, your first function is actually going to be cosine and the second one is going to be sine. So what that means is that when you look at this ordered pair over here, this number here is actually going to represent the cosine function at this angle, whatever this angle here, which they're actually calling it t. And then the second one is going to represent sine. Same thing over here. If you're looking at this angle, starting from the initial side to the terminal side. So that's going to be this entire angle. Well, it's still going to be the same thing. The first number is going to be cosine and the second number is going to represent the sine function. So that's actually what they're using to even help us come up with the initial values of sine and cosine. And remember what you saw in that little box earlier. Well, we know sine represents the y value. So if you have this ordered pair x and y, well, y is going to be the sine function and x is going to be the cosine function. So if you can first come up with what the sine and cosine values are going to be, then you can see this is just a matter of using the ratio of y divided by x divided by y, or 1 over x and 1 over y, and then you can come up with the remaining 4 functions. So honestly, it's just about starting with finding your sine and cosine as your first step, and that's exactly what they're talking about here. So when we're talking about the angle pi over 6, that actually means you've divided your circle into 12 equal parts, and this is your angle pi over 6. So that's the ordered pair where you have square root of 3 over 2 and 1/2. So we know that square root of 3 over 2 will represent the cosine function. 1/2 will represent the sine function. And you will see that's exactly how they've done this. So where did they go? There we go. So you can see from that they're coming up with sine of pi over 6 is going to be 1/2. Cosine of pi over 6 is going to be square root of 3 over 2. Then for the tangent function, we are doing y divided by x. So y is 1/2. X is square root of 3 over 2. Clean up that fraction. And then remember, any time you end up with a radical, not just a square root, cube root, fourth root, fifth root, it doesn't matter. If you end up with a radical on the denominator, you do have to rationalize your denominator. And that happens by taking that original fraction of 1 divided by square root of 3 and then multiply it by that radical on the denominator. So square root of 3 over square root of 3, multiply that fraction. 1 times square root of 3, of course, will just become square root of 3. Square root of 3 multiplied by square root of 3 on the bottom. So it's the same quantity, right? So you can do squared, kind of like if you did a times a, well, you end up with a squared. So that's the same idea. Square root of 3 multiplied by square root of 3 is square root of 3 squared. We know square and square root cancel each other out. And you end up with square root of 3 over 3. So that's how they came up with this fraction here. And guys, just to let you know, if rationalizing the denominator is something you haven't done in a while, go back to chapter P, right? That practice prerequisite chapter, and find some examples in chapter P to just help you kind of get comfortable, because this rationalizing part is going to happen a lot, especially in these first few sections. You're definitely going to see the rationalizing part. And if you leave it as 1 over square root of 3, technically that answer is incomplete. So you do need to go ahead and rationalize it. So please keep that in mind. Now, the other thing I want to highlight is how they are using this right triangle to also actually help us come up with these ratios for your 6 trigonometric functions. So as you will see here, they are saying we can use the 30, 60, 90 degree right triangle to find this point also. So, if you were looking at a new angle and you hadn't used that before, well, can anybody tell me what pi over 6 is in degrees? Because pi over 6, of course, is radians. What's pi over 6 in degrees? This pi over 6 is in radians. Since you are getting rid of radians, remember you multiply by the fraction 180 degrees over pi. So what will that come out to be in degrees? Nice, very good. Yeah, because pi will cancel out. 6 goes into 18 3 times, so that will actually become 30 degrees. So you can see why the 30, 60, 90 makes sense, because this angle here, 30 degrees, is the same as actually your pi over 6 angle. And by default, a 30, 60, 90 degree triangle always has this ratio. So you have, remember the hypotenuse, which is across from the 90 degree angle, is always going to be the longest side. So when they tell you 1 by 2 by square root of 3, remember square root of 3 is approximately 1.7 something. So square root of 3 is actually smaller than 2, but because it's easy to remember that order of 1, 2, 3, that's why they kind of write it like this, 1, 2, and square root of 3. But 2 is actually the largest number. So the 2 is going to go across from the 90 degree angle, which makes sense because the 90 degree angle is the largest angle, 60 falls in the middle, and 30 is the smallest angle. So the largest side has to be across from the largest angle, which also means the smallest side has to be across from the smallest angle. So that's why across from 30 is where you have the measurement of 1. 60 is in the middle, and 1.7 of course falls between 1 and 2. So across from 60, you have the square root of 3. And then, like I said, across from 90 is going to be the largest number, which is 2. So if you can remember that in the 30, 60, 90 triangle, your ratio will always be 1, 2, and square root of 3. Then, even if those ratios change, you will always be able to reduce them down and come up with these calculations. So once you can actually by default design this 30, 60, 90 triangle and place those numbers accordingly, then remember the sine function is opposite over hypotenuse. So this is actually where that S for sine, O for opposite, H for hypotenuse comes from. The cosine function is adjacent side over the hypotenuse. Oh. So that's going to be C for cosine, A for adjacent, H for hypotenuse. And then your tangent function is actually opposite over adjacent, because remember tangent is actually sine over cosine. So this is actually going to be T for tangent, O for opposite, and A for adjacent. So that's where that idea of SOHCAHTOA comes from. That actually helps you remember the order of these ratios. So now if we're trying to find out, well, what is the sine of pi over 6, which would be the same of sine of 30 degrees? Well, sine is opposite. So this is, this is my angle here. Then this is my opposite side. This is my hypotenuse side, and this is my adjacent side, right? So if you're going to be doing sine of opposite over hypotenuse, well, my opposite side is 1 and my hypotenuse is 2. And you will see that's exactly what we came up with for our sine of pi over 6 or 30 degrees, 1/2, right? And that was the same thing you had here in your ordered pair, because that's where your sine function is. Now for the cosine, and I'm going to change my color here. So for the cosine function of pi over 6 or cosine of 30 degrees, of course, I'm still using the same angle, but from this angle now, my adjacent side is square root of 3. And of course, my hypotenuse is still going to be 2. So that's going to give us the square root of 3 over 2. And you will see that's what we have here for the cosine function, square root of 3 over 2. And that's the same thing you had in your ordered pair over here, square root of 3 over 2 for the cosine function. So you can see there's a lot of that interconnectivity. You're using the ordered pairs like we do in algebra, but it breaks down into cosine as the first value in your ordered pair or the first coordinate, and sine as the second coordinate. And I tell you, the easiest thing to remember is if you even think in terms of alphabetical order, C comes before S. So that's how you can remind yourself that C is going to be in the X position and S, sign is going to be in the Y position. So that's kind of how you can remember, the order of those first and second coordinates in your ordered pair. Or as you can see, you can use that right triangle, 30, 60, 90-degree triangle to help you remember the ratios, SOHCAHTOA, TOA. So okay, how can I come up with these ratios? And if you look at that supplement I was showing you, that's exactly what this section here is talking about. You have this right triangle. And, in this case, we've kept it kind of generic. We're not doing this in terms of, 30, 60, 90, though that is one of the most common triangles we use. But, it's the same idea. If this is your angle over here, well, this is my opposite side, adjacent side, and my hypotenuse. So my sine is going to be opposite over hypotenuse, so that's your SO. Cosine is going to be adjacent over hypotenuse, so that is CA. Tangent opposite over adjacent, so that's going to be TOA. Now remember, these are the three main functions for trigonometry. The next three are the reciprocal. So I am literally inverting that fraction. You can see sine is opposite divided by hypotenuse. Well, cosecant is hypotenuse divided by opposite. So literally flip over that fraction. Cosine is adjacent over hypotenuse. So secant is going to be hypotenuse over adjacent. So again, you're just literally flipping that fraction. Same thing with cotangent, adjacent over opposite, and flip that fraction from tangent. So start by finding your sine and cosine functions. If you have those two, that can actually help you find the tangent also. If you don't have those, well, tangent also has its own definition, opposite over adjacent. Use that to find your tangent. And then once you have those three main functions, then, invert those fractions and you'll get the three reciprocal functions. And there you have it. You have your six trigonometric functions taken care of. So that's kind of how, these examples work out, is start with the sine, cosine, and then find the remaining four. And I've included some examples in here. Again, if you wanted to just use this as practice, this is not for homework, doesn't count for a grade. This was just extra practice to kind of let you guys get comfortable with some of this right triangle, based trigonometry, but otherwise you have enough examples in your homework and textbook if you just wanted to do it from here. So look through these examples here, just see how they are defining your examples, how they came up with that. And as you can see, they just started by finding sine and cosine. And then once they had those two, they used that fraction of, well, sine divided by cosine or opposite over adjacent, come up with my tangent function. Take the reverse of my sine. So 1/2 will become 2 over 1, which obviously just becomes 2. From the cosine, you can get secant. So this was square root of 3 over 2. So you can see we inverted that. But since your radical ended up on the bottom, we did the rationalizing of the denominator to move that square root of 3 from the denominator to the numerator. And then once you found your tangent function, then, of course, invert that and you would be able to find your cotangent. So these two are the main, then tangent. Once you have the three initial functions, go ahead and find the three remaining functions. I've included some other examples in here for you also to work with those. But before we get into that isosceles one, let's do an example for the right triangle over here. So let's get into section 1.2. I didn't mean to do that. Oh, right there. All right, let's get into section 1.2. Let me see. Which one do I? Let's do number 9, finding the point on the unit circle. So they're saying find the point X and Y on the unit circle that corresponds to the real number T. So if we're talking about, T equals pi half, think about that unit circle. Where first do you know the pi half is going to fall? Or you can always convert it to degrees if you're still not comfortable with the positioning of the radian angles. So where will our pi halves be on the unit circle?
At 90 degrees.
At 90 degrees, yeah, very nice. Andrew, yeah, very nice. All righty. So pi halves is 90 degrees. So, this is obviously, I picked an easier example over here. So think about a unit circle, right? We know this is at 0, 0. We know the unit circle has a radius of 1. So what will this ordered pair be over here? Because what's the X value? If you're right there on the, think of this as your X and Y axes. If you're right there on the Y axis, the radius of the circle is 1. So what will these ordered pairs look like?
0, 1.
Yeah, because your X value, again, Andrew and Lucy, yeah, very nice. And of course, I do want the rest of you to, take part in the answers also, guys. So, the X value on the Y axis is always going to be 0. And then because the radius of your circle is 1, this distance on the Y axis is going to be 1. If I had asked you as, I guess it's not in here, but if I asked you as T equals pi, so where your angle would be at pi, which would be this place right here, or 180 degrees. Well, if I asked you to find X and Y over here, then what would you say about this ordered pair here? Because now you're going to be on the X axis. So how will that change your ordered pair? Okay, I see Andrew, you've got -1, 0, and Savannah, you've got 0, 2. So the first thing, Savannah, to remember is since you're going to be on the x-axis, the x value actually is not going to be 0. It's the y value, which will be 0. So 0 will actually be here. And when you bring in the number 2, that means you are increasing your radius instead of 1 to a radius of 2. So the radius will actually not change in that case. Yeah, no problem. And so actually, since you are on the negative side of the x-axis, like Andrew had in his answer, you will actually be at -1. And guys, it's kind of like, think about, the number line. When you go on the left-hand side, it becomes negative. When you go on the right-hand side, it's positive. And then, of course, for the y-axis, when you go up, it's positive. When you go down, it's negative, right? So just keep that in mind as you're working with these ordered pairs for the unit circle. So that's kind of, and you can see there are other angles in there, other examples that you can work with, but I'm kind of trying to stick with some of the basic ones over here. Now, this next one is actually getting into now, you know how to find the values for your ordered pairs, but now let's find the functions themselves, sine, cosine, and tangent. So let's do an example from one of these over here. And what looks good? Let's stay with the positive angle for now, and then we can come back and do a negative angle, but we'll just start with 13. Your angle is T equals pi over 4, and you actually saw this same angle above in those examples that we were looking at. So where is this pi over 4 going to fall? Actually, I just realized, yeah, that this is a 45-degree angle because this is actually going to be halfway between the 0 and quadrant 1. Yes, Melanie, very nice. And this one, actually, we need to talk about the isosceles triangle for this. So I don't want to do the isosceles right now. I wanted to do the, these angles are, do you have anything positive over here? I guess pi over 3 is going to be our positive angle where we can use that 30, 60, 90 degree triangle. So let's just use number 14. Can you tell me what this angle is in degrees so you kind of know where to place it on the unit circle? Very nice. Yeah, and basically, remember this is kind of where you multiply this with 180 degrees over pi. So your pi will cancel each other out. And then you basically end up with 180 divided by 3. 3 goes into 18 6 times. So this guy comes out to be 60 degrees. So it's 60 degrees for pi over 3. So again, you can kind of eyeball that on your unit circle, and 60 degrees, is going to be more closer over here. 30 degrees was kind of in this direction. So this is the angle you are looking at for pi over 3. So this is where, again, you can use that triangle. And, it doesn't have to be to scale, but this is kind of, you can imagine, and, you can say, okay, you know what, I'm actually going to place my 60 degree angle here. I'm going to place my 30 degree here. And then, of course, this guy is going to be our 90 degrees. So remember, for your 30, 60, and 90 degree, the ratio is 1 to 2 to square root of 3. So across from the smallest angle is going to be the shortest side. So 1 is going to be here. 2 is the longest length. So that has to be across from the 90 degree angle. So 2 is going to go over here. And the square root of 3 always goes across from from the 60 degree angle. So that's where you are going to use. And Melanie, I just saw your answer. Yeah, very good. So, go ahead and create your 30, 60, 90 degree angle triangle with the ratios for those sides. And then now when we're talking about the sine function for this pi over 3, remember sine is opposite over hypotenuse. So remember, this is our main angle since we're doing this for pi over 3 or 60 degrees. So from respect to this angle, this side is the opposite side from the angle. Where you have the 1 is your adjacent side. And of course, always from the 90 degree across from that is going to be your hypotenuse. So sine is opposite over hypotenuse. So can you tell me what this ratio will end up looking like here for the sine of pi over 3 function? If you pick the numbers from the opposite to the hypotenuse side? Melanie, very nice. Yeah. Alicia, I'm guessing you meant to say square root of 3, but that looks good. Lucy, that looks good. Yeah, so remember your opposite side. Yeah, very good, Alicia. So yeah, your opposite side is the square root of 3. Your hypotenuse is 2. And that's literally all we have to do. Opposite over hypotenuse. Now, remember, if that square root was in the denominator, we would rationalize it. Otherwise, you don't have to worry about it. So this guy is good to go. Next, we will do the cosine function because remember they're asking us to do those 3 functions here. So cosine for the same angle. Now remember, cosine is adjacent over hypotenuse because that is so, and then CAH. So adjacent over hypotenuse. And what will this come out to be? Melanie, very nice. So your adjacent side is 1. Hypotenuse obviously is still 2. So 1 over 2 for the cosine function. Perfect. And then, I didn't space myself out properly. I guess I'm going to have to put the tangent function here. So tangent of pi over 3. Now remember, tangent is TOA. Man, I really didn't pace myself out. So TOA opposite over adjacent. And let's see, somebody has an answer here. Square root of 3, Melanie and Lucy. All righty, very good. So yeah, you can see your opposite side is of course square root of 3. Adjacent side is 1. So anything divided by 1 is the number itself. So you have square root of 3. So even though they didn't ask us for this, I'm just going to show you what those other three functions look like. So remember, for sine, the reciprocal function is cosecant. So if you had to do cosecant for that same angle pi over 3, this is where you would do the reciprocal of the sine function. So this would be 2 divided by square root of 3. When you rationalize this denominator, you would end up with 2 square root of 3 over 3. So this would be your cosecant function. Cosine, since cosine begins with a C, its reciprocal function begins with an S. So that's the secant function. And that will be pi for the same angle, pi over 3. So cosine was 1/2, which you invert that becomes 2 over 1. So this guy will end up becoming 2. And then same thing for the tangent function. Its reciprocal is cotangent, same angle. And since this guy was square root of 3 over 1, I'm just using that fraction from here. When you invert that, it becomes 1 over square root of 3. This one, again, we would need to rationalize the denominator. So that would be square root of 3 over 3. And I apologize, guys, that I did not like place myself out properly so you could actually see this a little bit better. But these are what your 3 reciprocal functions would come up with. So start with sine and cosine, then the tangent, and then you can invert those fractions to come up with the remaining 3 functions. So questions on this one? And again, you will really need to practice this a couple times to feel comfortable, because I know this is not like any other math you've done. So it can take a little bit of practice. So just be patient, work through a couple examples. And then obviously, if you get stuck, you need more help, I'm here for you. But anything popping up in your mind right now? Okay, you guys look okay. You look pretty calm. So I'm thinking you are doing okay, but if you start freaking out, please do let me know. Lucy, go ahead.
What if the degrees aren't 60, 30, or 90?
So that's when we would then have to actually bring in new math. And that's the next thing I want to talk about. So let's get back. Let me just make sure I save this. Let's get back to our handout. So the other rule you will see here is for a 45-degree angle. Sorry, yeah, an isosceles triangle. So, isosceles normally is going to be where you have the 90-degree here, and then these two angles are going to be 45 degrees. So you will see this actually has a ratio of 1:1 to square root of 2. And that's because, your triangle is technically 45, 45, and a 90 degree. So since these two angles are the same, then, of course, the two sides are going to be the same. So you will see from the opposite side of that 45-degree is where you have the 1 and 1 for your side measurements. And then the hypotenuse being the longest length is where the square root of 2 is. Remember, square root of 2 is approximately 1.4 something. So obviously that number is larger than the 1 and the 1. So that would be your 45-degree triangle. So that's actually where we can go back to number 13 and talk about what those functions would look like. So with our angle of pi over 4, this is of course 45 degrees. And this is what we were talking about, right halfway in that first quarter is where we would be at. So if you again did that right triangle, and of course, this is not to scale. And when I first started teaching, I would be embarrassed about my drawing, but as you can see, I don't care anymore. It looks like a kid's drawing, but you get the idea, hopefully, that I'm drawing a triangle and hopefully a right triangle. So with the 45, 45, and 90, it's ratio of 1:1 to square root of 2. So across from 45 will be the ones, and across from the 90 degrees square root of 2. But obviously, since you're using that right triangle trigonometry, none of that math is changing. So you are still doing TOA for those 3 main functions. So your sine for pi over 4 is still going to be opposite over hypotenuse. Cosine of pi over 4 will be adjacent over hypotenuse. And then the third one for those first 3 is tangent. Sorry, that should say tangent. Tangent would be opposite over adjacent. So go ahead and tell me what you think these ratios should be here. I mean, these fractions. And of course, you can use any one of these angles as your main angle since both of them are 45, it doesn't matter. But if you're, wanting to use this bottom angle here, that's fine. So you can think of this as the opposite side, adjacent side, and then this, of course, is the hypotenuse. So let's start with the sine function. What do you think that ratio should be? Yeah, very nice, Darren. So yeah, you have already rationalized your denominator because opposite is 1, hypotenuse is square root of 2. So when you rationalize that denominator, you'll end up with square root of 2 over 2. Perfect. What do we think our cosine for pi over 4 is going to be?
This is square root over 2 again.
Yeah, because obviously your angles are the same angle, and then that ratio still comes out to be the same. Yeah, very nice, Melanie. Andrew, I understand, not a problem. So the adjacent side is also 1. Hypotenuse is still square root of 2. So that ratio will also become square root of 2 over 2. And then what does our tangent come out to be?
One.
Yeah, because your opposite and adjacent are both 1. So 1 divided by 1 will give you 1. So those ratios, were taken care of. So now let's do the reciprocal ones. So again, sine starts with an S. So the reciprocal is cosecant, starts with a C of pi over 4. And what will this answer come out to be? And you can use this fraction if this is better. So for cosecant of pi over 4, what will we have? Yeah, because if you invert that fraction, you get square root of 2 over 1, which of course will just be square root of 2. For cosine, it begins with a C, so its reciprocal begins with an S, and that's going to be the secant function. Same, very nice, Melanie. Yeah, because they had the same ratio. So square root of 2 over 1 will, of course, still become square root of 2. So that doesn't change. And then the last one here would be cotangent. Yeah. So you can see this was an actually easier angle because even if I invert this fraction, well, it still says 1 over 1, which will still be a 1. So this is, your typical 30, 60, 90 triangle or an isosceles triangle. But as Lucy, you were asking me before, well, what if those are not, happy angles? So we'll definitely look at, well, what other techniques can we use to find those function definitions? Everybody okay with this isosceles triangle example here? Yeah, all right, perfection. Let's make sure we save this again. And let's get back to our handout. So you've got, a bunch of other examples, again, just because I like to give you enough examples that you're comfortable working with it. This one actually shows you with negative angles, how you can come up with those. And, this is going to be about direction because you're obviously going in clockwise direction if you have negative angles. So, look through these examples for the negative angle just to make sure you're comfortable. And then we'll actually pick up from here next time. I just want to talk a little bit about domain and range. And if you remember that from your college algebra course, domain is what are the acceptable x values that you can use in your function and what are the acceptable y values for your range, when you use those x functions. So we can talk a little bit about that next time and get into some of the other concepts from section 1.2 over here. But I'm hoping this at least gives you a good starting point for working into section 1.2 homework. So if you're still finishing up 1.1 homework, obviously go ahead and wrap that up, complete that, and then get into your section 1.2. And I did want to say something to you guys before I let you go. I just really kind of haven't had the time or the inclination to send an email, but we did lose my mother on Friday. We haven't had any funeral services for her yet. You know, the crematoriums are kind of backed up and stuff. So we're not sure when that's going to happen. And I'm not sure if I'm going to take time off or not, but since it kind of happened over the weekend and we've had some time to, you know, be together as a family and stuff, I kind of wanted to be with you guys here today. But, you know, if that changes, if I'm unable to continue teaching, my chair does have somebody to substitute for me. But if I can continue teaching, I will. So for now, I plan on being here Wednesday, but if for some reason I can't, I'll definitely email you guys in advance and let you know. Thank you, Melanie. I appreciate that. But keep in mind that, guys, we do have video lectures in your D2L course shell. So if somebody else does come in and teach, but you would still like to hear me explain the material to you, just remember there are video lectures in your D2L course shell. So you should be able to go and, you know, look through those, kind of work with those. And, you know, whenever I come back, you can definitely ask me questions and stuff. So I just kind of wanted to give you a heads up in case I do end up not being here for a week or two. But I will definitely keep you guys posted, and I will give you, like I said, a little bit of an advance notice to let you know if I'm not going to be here. But for now, I do plan on being here on Wednesday. Okay. So I just wanted to let you know. And I have been receiving emails and messages from you even in the past week after I'd sent out that first message. And I really wanted to say I appreciate the kind words you've been sharing with me. So thank you very much, guys. And don't hesitate to reach out. You know, don't think that because this is happening, I will not get back to you. Like I had told you before, it may take me some time to reply back, but I'll definitely reply back to you guys. So don't hesitate to at least send an email out, okay? All right, I'm kind of sorry that I'm leaving you with that note, but you know, I wanted to get through the class before I told you guys about that. But just, you know, hang in there. We will do our best to make sure you don't have too much of a break in your learning, but we're all going to be here for you. If I'm not here, my chair will make sure we have a good instructor to step in for me, okay? All right, everyone, well, have a wonderful evening. Take care of yourselves, and I'll see you on Wednesday afternoon. Take care, everyone. Be careful. Stay safe. Bye, guys. Thank you, Savannah. I appreciate that.
Really sorry to hear that.
Thank you, Kevin. I appreciate that.
Is it so is this your you will be here for Wednesday's class?
For now, I plan on being here for Wednesday's class, but if anything changes, I will send you guys an email at least by Wednesday afternoon to let you guys know.
Okay. And are you after Wednesday's class? Will that will be your last class with us?
I'm not sure. I haven't made up my mind yet because, like I said, you know, there's a lot of backlog coming from the funeral home. So we're not sure when the services will happen. That's kind of why I'm not taking a break right now, because honestly, we have nothing to do till they tell us when, you know, they will be performing the services. So I'm kind of waiting to hear back from them. But yeah, for now, I'll definitely be here Wednesday. And if I have more answers for you, I can let you guys know if I'll be here on Monday next week or not.
Okay, thank you.
Yeah, you take care,
All right.
Kevin.